So we were looking at this theory, which is Phi-4 theory. Let me write down the action. Okay, note that here when we were looking at free theory, m turned out to be the mass of the particles in the theory, right? And because we could construct states and show that the states were labeled by momenta, we satisfied the dispersion relation p square equal to m square, and that's how we identified that this m which appears in the Lagrangian is really the mass of the particles. Okay. But there is no reason that this should turn out to be the mass of particles in this theory when you have this term also present. Okay, so that's one point I want to emphasize. I don't think I will have time to go into details of finding out the physical mass in this theory, but if I denote by mp the physical mass, okay, so meaning you in this theory, so you expect that in this theory you will have single particle states, right? And those single particle states will have some mass, which I call mp, p for physical. Okay, there is no reason that this should hold true. I mean, there is no reason that mp should be equal to m. So in general, mp will not be equal to m, and in fact the physical mass would be some function of m and lambda. Okay, and if you were to take lambda to go to 0, then of course physical mass will go towards m. So physical mass will go towards m if lambda goes to 0. Okay, but in general and in the interacting theory, the coefficient of the quadratic term is not going to be the physical mass. Okay, so that is one thing we should keep in mind. Now let me write down the Hamiltonian with which we are going to work mostly. So you have half pi whole squared, okay, plus half gradient of phi. I will suppress the arguments of phi, okay, plus half m square phi square. Okay, so this is one term, plus you have another term, let me make it more explicit here. Okay, so that's the interaction term, and this part I will call h naught. So this is by definition h naught. This is h interaction. Okay, so these are the names for these two terms. So I write h as h naught plus h interaction. Okay, and also remind you that we have been working in Heisenberg picture, where the fields evolve with time. So if you start with the field at time t naught, okay, at position x, and you want to reach to time t, then this is how you do it. So these are the unitary operators that take you from phi at t naught to phi at t. Okay, where h is the full Hamiltonian, and similarly for pi, the same factor here and the same factor there. Okay, now remember that h is a conserved quantity, the full Hamiltonian, because that conservation follows from time translation, but h naught is not a constant of time. Okay, because h naught is not something that follows from the conservation of translation. Okay, that's not a conserved charge. Okay, So h is a constant of time, but h naught is not. Right, so there is no conserved charge that is equal to h naught. It's the h. Okay, so now what I will do is I will take the field configuration at some time t naught and also the momentum density configuration at some time t naught and evolve it with free part of the Hamiltonian with h naught. So what I do is I take field configuration or the operator at some time t naught. Okay, actually I should say operator. Okay, these are operators now, and similarly I take pi at some time t naught, the momentum density operator, and instead of evolving it with full Hamiltonian, I evolve these two operators with the free Hamiltonian. Okay, so I do this. Now why this is going to be useful you will see soon, but I can do so. I can choose to do this, so I will do that. And of course these are not the same as phi and pi because they evolve with full Hamiltonian, and this is something new that I am constructing, so I give them names. I call this object as phi I and this object as pi I. Okay, so what is phi I? How do you get phi I? Phi I is the operator, okay, which you get by doing this. So if you take the operator at time t naught, the phi at t naught, and evolve it the free part of the Hamiltonian, then what you get is phi I, and similarly for pi. Okay, so that's the definition of these two operators, phi I and pi I, and they are called interaction picture field and interaction picture momentum. So this phi I is called interaction picture field operator. Okay, I stands for interaction. Okay, so this is my definition of phi I and pi I. Okay, so what I have done basically is started with an operator and evolved it with free Hamiltonian, and the reason I am doing so is because I know how to deal with fields and momenta when they are evolving with free Hamiltonian, because they are the ones which are described by free theory, right? So fields in free theory will evolve exactly like this. See, it doesn't, I mean, the fact that there is a phi instead of some free field here doesn't matter, because after all it's some field, right? Some operator. What the theory tells you is how it evolves with time, right? So I start with some operator and I arrange the evolution according to free theory. Okay, so that's why what I have done here, and that is useful because I know then how to deal with phi I and pi I, right? Because they are just like free operators in free theory, right? So if they are operators in free theory, or they are like objects of that form, then I would expect that they also satisfy commutation relations as they did in free theory. Okay, and that is something we can also check. So let me write, since phi I and pi I behave like or evolve like evolve as the field and momenta, conjugate momenta, which conjugate momentum I mean, I don't mean physical momentum, momenta in free theory, we expect that they will satisfy the following commutation relations. That if I were to construct and that is the expectation that we will have. So this we should expect to be 0. So these are equal time commutation relations. And I should expect that if I take phi I t x, phi I t x prime, I should get I delta cube x minus x prime. And let's check whether these expectations are met. So let's check this one, and the others will follow similarly. So let's check the third one. So I start with the field phi at t naught x and pi t naught x. So these are the operators in full theory, okay, and this is an equal time commutation relation, and that equal time commutation relation has to be this, because that's how we quantize our theory. Okay, now I will turn it into expression of this form, and that is easy. All I have to do is bring in these factors. See, phi I has a e to the I h naught t minus t naught on the left, and e to the minus I h naught t minus t naught on the right. Okay, and this the inverse of this factor is just the same thing with the plus sign, right? So the inverse of this is e to the plus I h naught t minus t naught. So I will use this, and in this expression I will multiply on left with e to the, what was that, I h naught. Okay, and on, okay, again I have written wrong, L E F T, and on the right I will multiply with e to the minus I h naught t minus t naught. Okay, so here you have phi times pi minus pi times phi. So let me write here, you have phi pi minus pi phi, and in the middle I will insert e to the minus I h naught t minus t naught, e to the I h naught t minus t naught, which is 1, right? This is 1. These two factors cancel and give you 1. So I will insert in between 1. So when I do all these things, I get e to the I h naught t minus t naught. Okay, then you get a phi t naught. Sorry. Okay, then I will insert this h naught t minus t naught, h naught t minus t naught. Then you have the factor of pi. Okay, and then on the right you have multiplied with this one, so you get this. Okay, and minus the same thing with phi and pi interchange. Okay, now you see this factor here, that's precisely phi I. Right, we can go and check this with the plus I, minus I, with the phi at t naught. So that is phi I, this piece, and this piece is pi I, right? And the thing which you are subtracting is exactly the same thing in reverse order. So what you get is phi, I t x pi I t x, and this commutator. Okay, and what has happened on the right hand side? On the right hand side I have multiplied from left this object and right this object. Delta cube is this entire thing is a complex number, so that doesn't interfere with these operators. So these two operators can be brought together and they just kill each other and give you 1. So this factor remains. Okay, so indeed the commutation relations are exactly the ones which the free theory satisfies, or even in your full theory, the same commutation relations are satisfied. Okay, so this is good, and this is good because we know how to deal with fields which evolve like free fields, okay, and the operators which evolve like free operators. So we will be able to do exactly what we did in free theory. We will be able to define a vacuum which is annihilated by A's and A daggers. We will be able to introduce them, okay, because our fields are behaving like free fields, and the entire machinery that was developed in the case of free field theory can be used here, provided we can express everything in terms of phi i's and pi i's. If we can do so, then we can get some answers. So now our task is to look at the operator phi and try to express it in phi I and pi I. Okay, so that's the goal. So as I said, we want to express everything in phi I and pi I, and because these are the objects we know how to deal with. Okay, so let's see. Okay, now that is not difficult. Let's start with phi. Okay, the field in the interacting theory, and you know how it evolves. Okay, that we wrote some time back. Let me write it again. That's full Hamiltonian. Okay, now what I will do is I will insert in here and in here identity in this form. Okay, that's what I'm going to do. So this becomes, let me start with here. So let's see what we have to write. So I want to have plus IH naught in the left. So I write e to the IH naught t minus t naught, but then I should kill it, and this guy is there. Okay, and similarly here I should put minus IH naught, but then I should kill it, and you have this guy here. Okay, now this is our phi I. Okay, and this is fine, and I define this to be, I give it a name, this operator u of t naught t, and this you can then see that this is just the dagger of it. Okay, see, H naught and H are both Hermitian, so when you dagger, only the sign of I is going to change and the order is going to change, and when you dagger this one, this guy goes to the left with a plus sign, and this is exactly what you get here, and this guy becomes the second one. Okay, so this is u dagger t naught t, and as you can see, u is unitary. That's why I'm using the symbol u, because if you were to multiply this factor with that factor, you'll get 1. Okay, so what I have achieved is that I can write phi t of x as u dagger which is not appearing to be something very spectacular, because we wanted to express phi's in terms of phi I and pi I, but what we have here is phi is in terms of u and phi I, but u is made out of the h0 and h, and h0 and h are constructed out of phi's, right? h0 is this, so it is made out of pi and phi, and h is also the full thing, so it is also made out of pi and phi. So we have not really gotten what we wanted to, but then you will see that I can express u also in terms of phi i's, okay, and that will solve our problem, and we will be able to express phi completely in terms of phi i's. Okay, so let me write here. In the same fashion, you will get the following. So now our issue is to do something to u to turn it into an expression involving only phi i's. Okay, so that's the task. Okay, so let's try that. Let me write what u is. U is this. What was the u? IH0 and then minus IH. IH0 and then e to the minus IH t minus t0. Okay, remember these two exponential, they do not commute. You cannot just take this one and put to the left. See, these are operators, right? The h0 is made out of field operators, phi's and pi's, and similarly the h. Okay, and if these both were h, then it's another thing, but right now they do not commute, right? Because h0 is different operator from h operator. So you cannot reverse the order, that you should keep in mind. Okay, so anyway, that's the expression of u. Now what I'm going to do is, I'm going to find out a differential equation that the u satisfies. Okay, and I will provide a boundary condition and to solve for u in a different way. But as you will see that when I write down the differential equation, I will have something nice. I will be able to turn the entire u into only expression involving only phi I. So let's do this. So let's multiply with I and take a derivative of u with respect to time t. Okay, I am putting a partial derivative because u is a function of both t and t0, and I am taking a derivative with only t. So let's see what it gives. So when I take a derivative here, it will give e to the IH0 t minus t0 IH0. So I am differentiating this one, I get this H0. Now this H0 you can put that side or this side, doesn't matter, but it has to be before this vector, okay, because they do not commute. And then when I take the derivative on the second term, it gives me IH0 t minus t0, that pulls out a minus IH, and e to the minus IH t minus t0, and I have been forgetting to multiply factor of I. Okay, so I square is minus 1, and this one will have plus 1 because minus I times plus I gives you plus 1. So I can write the above expression as the follows. Now this is getting very useful. You will see immediately why. So this is e to the IH t minus t0. This is the interaction part, right? This is actually the following: d4x lambda over 4 factorial phi x to the 4th, right? That's the difference of h and h0, and you have this factor e to the minus IH t minus t0. Okay, so till now it does not look like much has happened, but now what I will do is, at this location I will insert e to the minus h naught t minus t naught and into the I h naught t minus t naught. So that's the factor I am going to insert in here, and I get the following: h interaction, the interacting part of the Hamiltonian, then you have e to the minus I h naught t minus t naught I h naught t minus t naught. So that's identity. I have done nothing, that's multiplying 1, and you have then e to the minus I h t minus t naught. Okay, now if you see this part, this is containing h interaction, which is just this. So you have field 4 factors of field phi, and there is some lambda over 4 factorial d4, sorry, it should be d cube x. Okay, so what these factors, these operators on left and right will do is, they will turn your phi into phi I to the 4th. Okay, that you can check. So this changes h interaction into something we write as hi, where hi is defined to be h interaction, and where when you take the expression of h interaction, interacting part of the Hamiltonian, you replace the field phi by phi I, and if there were any pi's in the h interaction, you replace them by pi I. But of course in our case we do not have a pi here, so this is the only relevant piece, but in general that is what you would do. So you get hi, I hope you agree that this gets turned into hi, times this piece, right? And let's see what this piece is. This is exactly what you have in here. This is u of t naught or t naught t, whichever way you read. So what I have got a differential equation I del u over del t equal to hi u of t naught t, right? So it's a differential equation for u which involves hi, and hi is constructed out of phi i's. So when you are going to solve for u using this equation, the solution will involve only phi i's, right? And that is what we wanted to do. So here, if I get a solution of u in terms of phi i's, and then of course u dagger will also be in terms of phi i's, okay, and then the entire right hand side will be completely in terms of phi i's, okay, and that's what we wanted to achieve. And of course you will need a boundary condition to solve the expression for u. So let me also give that to you. So where we are, we have found that I del u over del t okay, where hi, as I wrote just now, in this case is d cube x lambda over 4 factorial phi I x to the 4th. Okay, and to uniquely determine the solution you need boundary condition, and that's easy. You can check that u of t naught is 1, and let's see. Okay, sorry, where is it? Yeah, if you put t naught here, that becomes 1, this becomes 1, so u of t naught t is 1. Okay, so we are almost there as far as solving phi in terms of phi I is concerned, and we will continue from here in the next video. Okay, so this is one thing, and yeah, and I should remind you that it's not the only phi which we have to worry about, it's also the omega, right? this is also not yet in terms of free vacuum and free operator. You still have an H here, so we still have to do something, but we were almost done because we had free vacuum here. Okay, so yeah, I think I should write e to the minus IH lambda minus epsilon, e to the minus IH lambda minus I epsilon times some factor, some constant, some factor here n, and this is what we have found till now. Okay, let's check if it is correct. This is correct, and of course I should put lambda going to infinity followed by epsilon going to 0. Okay, so this is where we stand right now. Okay, that's our boundary condition. Okay, when you have a differential equation, to get a unique solution, you need to have a boundary condition. Okay, and that's our boundary condition. This is first order differential equation, so you need one boundary condition, which is here. Okay, so things have started looking good now, and in the next video we will try to get everything in terms of phi i's and free vacuum, and then we will be in business. Okay, see you in the next video then.